Okay, so we know for step one, we simply want to extract one shell that we're going to integrate over. And we know how to do that. We just split the measure into two pieces and we integrate over the high energy modes. For step two, which involved actually looking at that integral, we've learned that step two will generate all sorts of new terms in S effective. In fact, in general, we'll generate every term that's consistent with the symmetries of the theory. So what symmetries would we have? Well, we'll definitely have Lorentz invariance always. So the terms that are generated would be Lorentz invariant. For the phi-4 theory that we were studying, we would also have a symmetry under phi goes into minus phi. And then finally, we've also seen that at weak coupling, step two doesn't necessarily generate very big effects. So at weak coupling, the effect generated by step two can actually be very small. So now we just want to discuss step three, and then we know how to perform the whole process. So let's see what happens inside step three. So in step three, remember here, we want to compare S and the effective action S effective. So we imagine we're calculating some correlator. So this is equal to an integral d phi. This now measure has a cutoff, lambda, e to the minus s, and we would have whatever fields are in the correlator, also in the integrand. And this is also equal to the integral over d phi less than e to the minus s effective with the fields again of the correlator again appearing in the integrand. So this really means we are comparing integrands, okay? So we're comparing integrands. Oh, let me just make one comment in case you get a little bit confused. Don't forget that inside the correlator, only phi less thans appear. So all of the fields in the correlator can be taken out of the integral over the high energy mode. So don't let that confuse you. Okay, so here we're comparing integrands. You know, if we want to compare integrands, it's only meaningful. So the comparison is only meaningful if the integration domains match. Okay. And that should make sense. We know that the result of the integral will be the same. If we're integrating over the same integration domains, then it's meaningful to compare the two integrands. Okay, so what are these domains? Okay, well, we know what d phi lambda is. This is product. We're going to integrate over all modes that have a mod k less than lambda d phi of k. So good, that's fine. What about d phi less than? Well, d phi less than does look different. This is equal to a product over all modes inside a slightly smaller shell, 1 minus b times lambda d phi k. So the shell is definitely smaller. Well, I'm going to consider a rescaling of the momenta. Let's put k primed equal to k over 1 minus b. The biggest k, so if we look at k biggest, this will be equal to lambda. Okay, that's the biggest momentum that we're allowed, times by 1 minus b. Okay, so I'm looking at phi less than, that's the biggest k that's allowed. So what's the biggest k prime? Well, the biggest k prime will be the biggest k over 1 minus b, and that is just lambda. So if we write our integration measure in terms of k primed, in fact, k primed must be less than or equal to lambda, and now we scale d phi of k primed. So that means what we've just argued for here one way to say it is that we should only compare S and S effective after rescaling K to K prime. Okay, that rescaling between K and K prime. So this is the rescaling that we have to do. Maybe it's much better to state it just in terms of the rescaling equation. Good. Okay, now remember, H bar is fixed to be equal to 1. And if H bar is fixed to be equal to 1, then positions are like inverse momenta, and momenta are like inverse positions. So we should also rescale positions, but by a factor of 1 minus b. So it's the opposite scaling to what you see for the momenta. So that's the other scaling that we have to do. And finally, we should ask, how should the field be rescaled? Now, here I'm going to appeal to something that we did when we were discussing renormalization. We said that we like to have the field normalized so that it creates a particle probability equal to 1. And we already found that that meant that the kinetic term in the action should just be 1/2 d mu phi d dx. So I'm going to continue to require that. So I would like this to be equal to integral 1/2 d prime mu. So this is d by dx primed, phi primed. This is d by dx primed, phi primed, d dx primed. And this, in fact, determines everything. So let's see why. So first of all, how does d by dx relate to d by dx primed? Well, you can go ahead, just use the chain rule. We know how the x's are related. I'm just going to state what the answer is. You get a factor of 1 minus b sitting there. That makes perfect sense. It's scaling exactly the as we would expect. So thinking about this as the momentum k, this is equal to 1 minus b k primed. And that's completely consistent with the scaling law that we saw for the momentum. So that's exactly what you should expect. Check it with the chain rule. It's entirely obvious. Good. And then we also need to work out how does d dx transform. And in fact, well, okay, so let me write down the answer and then maybe explain it. So this is 1 minus b to the minus d dx prime. And what would you do? You just calculate the Jacobian here. So this factor over here, I'm claiming, is the determinant of dx I dx prime j. So go ahead and calculate that determinant, and that's exactly the answer that you'll find. So if we plug that in, I'm now going to look at this side over here. So I'm looking at this side over here. Let's see what this gives us. Let's plug these results in. So we'll have an integral of 1/2. If we want a d primed sitting here, then we need to include these 1 minus b's. So we've got a 1 minus b squared, and now we know that it will be a d primed mu phi, d primed mu phi. And then if we want to have a d dx primed, then we need an additional minus d. And we can rewrite this as follows, an integral of 1/2 d mu prime, and then we can put in 1 minus b to the 2 minus d over 2 phi, and a d mu primed 1 minus b to the 2 minus d over 2 phi. So I've just split this factor into a product of two terms and associated one with each of the fields. And now comparing this expression that we want to this expression that we've got, everything matches. the derivatives with respect to x prime, we're integrating dx prime. So we can now identify phi primed with 1 minus b to the 2 minus d over 2 phi. Great. So that's how the field must be scaled. So this is wonderful. We learned how the field scales, we know how the momenta scale, and we know how the position scale. And why have we done this? We want to compare S to S effective, which is comparing two integrands, and that comparison is only meaningful if we are integrating both integrands over the same integration domain. Good. Let's explore the scaling law a little bit further, and we'll do that next.